Stirling engine is an engine that operates based solely on temperature difference. This team uses a solar collector to provide the heat to power their engine. This engine can run emissions free. Up next we have the Solar Stirling engine team.
Good morning, everyone, and thank you for coming out to the symposium. We are the Solar Stirling Engine Group, and I'm Matt Bartow.
I'm Joshua Carlson.
I'm Daniel Schaefer.
I'm Robbie Ribbons.
All right, before we go on, we'd like to give you a little background to give you an idea of what the Solar Stirling engine is and hopefully pique your interest. A Stirling engine is a heat engine. Oh, we got an issue. Is that, you see that? Oh, I'm sorry. A Stirling engine is a heat engine that operates by cyclic compression and expansion of air or other gases at different temperature levels. The engine is capable of converting heat energy into mechanical energy. Now, the beauty of this is that we don't need any sort of combustion as an internal combustion engine, and we only need some sort of heat source to run our engine, and in our case, that's the sun, which is free. It's also low maintenance cost and has longevity. The reason for this is that all of the mechanical parts within this engine run at the cold side of the engine. That means there's no high temperature. It's not having any issues with friction or wear that your normal internal combustion engine would have. Now, the purposes and goals of our group are to explore an alternative energy source, which is the Stirling engine. We would like to optimize our heat, viewing dimensions as well as the material selection. Stirling himself, 200 years ago when he first invented the Stirling engine, had basically set parameters for ratios of displacement and power cylinder sizes and sweep volumes. And using these and also our background in engineering, we chose certain materials based on their thermal retention and their thermal conductivity in order to create the best transfer of heat and hopefully a large amount of efficiency and power output. We'd also like to look into working fluids. Our current design is going to work with air, and if given the time, we would also like to test helium. Helium, with the structure of the atom, will allow it to transfer more heat, and even also if you were to pressurize it, that would also increase the efficiency of the engine. We'd also like to test our proof of concept that the efficiency of a Stirling engine is not only high, but could be considered comparable to photovoltaic cells or any other alternative energy source. One of the ideas that we're leaning towards is to focus on the increase in the temperature difference. Now, this is what we want to do is we'd like to put it into a body of water, float it, and then have the cold side cooled by the water, giving the largest temperature difference we can get. And ideally, because the ocean is not populated, we can find remote areas that won't be impeding any boat traffic or anyone else, and it could just sit there and just farm energy, and you could just bring it all in and hold it and transport however you'd like. And finally, in the end, when we're doing our testing, we'd like to perform our engine efficiency analysis. And to do this, we have a torch that we would like to heat up the hot side at a desired temperature, and then that simulates the heat so we don't have to worry about losing the sun and suddenly we can't heat our engine. And then we calculate the power output and hopefully reach above 30–35% efficiency.
This is a CAD picture of our engine. The red side is the hot side, which is made out of steel, and the blue is the cold side, which is made out of aluminum. Basically, our engine was designed to ASME boiler and pressure vessel standards, so the flanges and the bolts were selected for that purpose, and so they could withstand the pressures we achieved during our cycle. So our future applications, we like to harness renewable energy with little impact to the environment, with no CO2 emissions. And we'd like to eventually hook up a generator to our shaft and actually create power, since we're just testing actual mechanical output of the engine right now. We'd also like to make an economical alternative energy source with efficiency that surpasses photovoltaic cells. So this would be much cheaper since there's low maintenance cost, and you can basically get a really low friction generator and create high efficiency energy. Also, this could be used for off-grid power applications in remote locations as well. So
we are the Stirling buoy, the Stirling engine group. We originally had a buoy, but budget didn't allow that. My name is Matt Bartow again. I was the team leader. I focused on the overall design and solar collection. This was Joshua Carlson. He was on the mechanical side, as well as he did all of our CAD modeling very well. It's beautiful. We've got Daniel Schaefer right here. Daniel was with me on testing for solar to make sure that we could reach the temperatures we'd like to achieve, as well as all the heat transfer calculations and power calculations. And finally, we have Robbie Ribbons, and he was into mainly our research materials, and he did all the calculations for the ASME boiler standards on our displacer. And we'd like to thank Progress Energy for the funding and all of their support, and UCF, Dr. Gao was our faculty advisor, and our technical advisor was Dr. Coffey. Everyone's been very great. We're grateful for all their help, and we thank you for coming.